Okay, hello. Hello everybody and happy Friday. I decided to be a floating head today. um I guess floating head and floating hands. All right, let's get started. Okay, we're doing a cool stuff live stream today, and I have a very special guest today. Gemma Israf is with me, though I will bring her on a little bit later. We're gonna talk about the project that we've been working on first. Also, good morning to everyone good morning to everyone where it is morning. It is very morning for me. But I thought I would start a little bit earlier since I feel like everybody in the world is basically east of me. So when I do cool stuff live streams at noon, like everyone is asleep already, but whatever. All right, so let's do cool stuff streaming today. Where are my slides? Come back here, Keynote. All right. So today we're going to look at a project that Gemma, Eileen, and I have been working on at Shopify, and it is called Object Shapes. And we're going to talk about what that project is. Oh, 6 p.m. there. Okay. And by the way, if anybody watching this, please feel free to put questions into the chat room, and I'm totally happy to answer them. So just throw them in there. So let's talk about this project. What are object shapes? I think that's a decent question to ask first. Object shapes are not actual shapes. They're not real shapes. It's just a concept, like a thing that we think about. It's a way for us to represent object attributes. So it's a way for us to represent or say some particular object has particular attributes on that object, or just different attributes describing the object itself. And I think the main or the biggest example, or the easiest example, and the example that we're gonna go through today is instance variables. So we're gonna focus on instance variables, or implementing instance variables using object shapes. So these shapes, they're just regular Ruby objects as well, but they form a tree data structure. So these shapes form a tree data structure, and edges in the tree are transitions. So we're going to see this in action in a little bit, but just know that they form a tree, and that edges in that tree are transitions. The other thing that we need to know before we get into the actual instance variable implementation is that instance variables are stored in an array on objects. So we store all the values for instance variables inside of arrays. So for example, if we had some Ruby code that looks like this, we have an instance of foo, and that instance of foo points at the foo class. Happy Friday. The instance of foo points at the foo class, and then the instance points at an array, and that array contains the values for the instance variables. And one thing to notice here is that these instance variables, there's nothing here necessarily mapping 1 and 2 to the names A and B. So we have to have some way for us to map A and B to 1 and 2. So we have to have some way of mapping those names to the values. And that's kind of what we're going to take a look at with shape transitions here. So let's look at how these shape transitions work, or how the shape tree is actually formed. So say we have some code like this. We come in, we have a foo class that has 3 instance variables on it. And we're going to walk through slowly how this program executes. And when we first enter the initialize for foo, this particular instance it starts off at the root shape. So this is shape 0. It has every object when it comes alive is associated with the root shape, so it has no transitions off of it. So the first thing that happens is we want to set the instance variable A, and when we set that instance variable, we try to ask, like, what is the index of A? Well, at shape 0, we don't know it. We don't know about A, so we have to make a transition to the next shape. We say, okay, we're gonna add the instance variable A, and by adding that A, we'll transition to shape 1, or the next shape. In this case, it's just shape 1, and we'll keep a map of the instance variable name to the index. And since we've never seen A before, A will go to index 0. So then we go on to B, and we try to set B, and we do exactly the same process. We don't know anything about B, so we have to create a new transition from 1 to the next shape, which in this case is 2. Shape 2 will map B to 1 because we already have something, like this is our next one, essentially our next one in the list. And we repeat the process with C. So again, we map C to 2. Now, after we've executed all of these, like each time we execute these, we keep an inline cache in that particular area. So once we've executed A equals A, or at A equals A, we store the fact that at that time, we were at shape 0, we transitioned to shape 1, and the instance variable index at that time was 0. So we cache all of those values. So let's take a look again, but this time, the second time we execute initialize and walk through the code. So this is the second time we go through initialize. The second time we come through here, we're at shape 0, and we look at the inline cache and we see, oh, we know this shape 0. We are shape 0, and we don't need to look at the tree anymore because we know that shape 0 goes to shape 1, and this particular instance variable is stored at position 0. So we hit this cache, and it transitions the object to shape 1, and we go on to the next case, B, and here our cache key is the shape. Again, we're at shape 1, we know we transition to shape 2, and our instance variable is 1. So we cache all of these values so that we don't have to look through that tree anymore. And it just goes through these cases again. Okay. So the cache key, the important thing is that the cache key in this case is the shape ID. So whatever ID we've assigned to that particular object, that is our cache key. So let's take a look at another example. This is a transition, but let's say we have some branching code in our initialize. So in this case, we'll come in, again, our entry is 0. We set A, we move to shape 1. We set B, we move to shape 2. We set C, we move to shape 3. And this is very similar to the previous example. And we cache all those values as we go through this, execute this code. Now in the second case here, we've said that swap is now true, so we're going to take a different branch in the if statement in initialize. So when we come through and we set A, we're at shape 0, and we actually get a cache hit here, so we hit on this cache. But now we have to come into this if statement, and in this case, we have to set a new shape ID because we don't have a transition from shape 1 to some other shape via that instance variable name. So those keys are important, or the names of the instance variables are important as we transition through the tree. So we'll go here, we'll create C goes to shape 4, B goes to shape 5, and we cache all of these values. So if we were to look at the shape ID of these two objects after we've executed these, this first instance will be a shape ID 3, the second instance will be shape ID 5. And the important thing here is that what matters is the order that we set the instance variables on the object. That's the important piece here. All right. So why are we doing this? This seems like a lot of work. Why would we add all this complication into the code? And the reason we would do this is because it impacts our reader and writer performance. So this is a way for us to speed up reading and writing instance variables. But how does this possibly speed up reading and writing instance variables? Well, in order to describe that, I want to contrast this technique with the technique that's currently being used in Ruby today. The technique currently being used is that we associate instance variable indexes with the particular class that we're on. So we're looking at today's, what's implemented today. In today's implementation, the instance variable index is stored on a hash, And in this case, let's say we execute this code, we'll look at the foo class. This index, the name value index, is stored on the instance variable to IV index hash table is stored on the class itself, not the instance. So we'll say, oh, we need to find a new index for this. So we'll go to the foo class. We look in the foo class's hash table. It doesn't have one, so we add one at index 0. And then we do the same thing with B. We add one at index 1. We do the same thing with C. We add one at index 2. And then we cache all of these values as well. So today there is an inline cache for these instance variables, but our cache key is actually the class itself. So we do cache all of these, and the next time we execute this, we'll say, oh yeah, it's the same class. It's class foo. We hit, so we know the index. So the cache key is the class. But what happens if you have, say, a subclass, for example? So in this case, we have foo, and then bar is a subclass of foo. So when we execute foo, the inline caches will contain foo as the cache key along with the instance variable index. But then, unfortunately, when we execute bar.new, those caches all fail because the class is different. So what's interesting here is that shapes really only care about the order of transition. So they only care about what instance variables we went through, that order of instance variables. They don't care about the class at all. So if we contrast this, like let's say we have a shape object shapes implementation. In this case, we'll execute foo and we'll create this shape transition tree. And then when we execute bar, we hit on all of these caches because we don't really care about the class at all. So what's cool about this is it applies to both reads and writes. So shapes they're able to hit on reads and writes where the current implementation cannot. So let's take a look at the IV set. This is pseudocode for setting an instance variable. Now, it's kind of hard to read. Like, the main difference here, I'm going to highlight the main difference, is right here where the existing implementation checks the current class to see whether or not we've hit that cache. Whereas in the shapes implementation, we're just checking the shape ID. And in fact, we can do even better than this. Any attribute of an object can be considered a transition. We don't have to just think about instance variables. That's not the only attribute that we can use. We can have other attributes. Actually, let's do. Sorry, I want to mess with this green screen more. Any attribute can be a transition, including freezing. So let's take a look at freezing. We can say that freezing an object will introduce a transition. So for example here, we'll say we create foo. After we execute foo, we'll set a. So when we called foo.new, we're at shape 0. We say set a transitions it to shape 1, and we add an inline cache in this particular case. I know I want a green screen microphone so badly. Yes. I was like shopping for green screen tape. All right, sorry. So we'll cache that we made a transition from shape 0 to shape 1 and that the instance variable index is 0. So now in this case, like this one's a little bit different because we're freezing before we actually set the instance variable. So we'll freeze. We're at shape 0. We say, all right, we're going to do a transition from shape 0 with an edge for freezing. So freezing becomes an edge in this tree. So we'll introduce a new edge here, and we'll call that shape 2. It could be any number, but let's just say it's shape 2. And then when we say set A will come back, and when we try to set that instance variable, remember the shape ID is the cache key. And in this case, our cache keys don't match. So we have shape 2, and we had cached shape 0. So those cache keys don't match, and when we have a cache miss, then we can just check the freeze status. So frozen checks only need to occur when we have a cache miss. So we can change the code to look like this. So in the current implementation, we have to check every single time we set an instance variable, we have to check, is this thing frozen? Whereas with the shape implementation, we only have to do it on a cache miss. So the current implementation always checks for frozen, whereas a shape implementation only needs to do it on a cache miss. So I've highlighted the code here. Again, you can see like at the top there, we're always checking frozen versus a shape implementation where we only need to do it on a miss. So with the shapes implementation, we're able to get more cache hits and fewer runtime checks. Now, the next thing I want to talk about is shape IDs, and this is a part of the project that we've been having a little bit of trouble with, kind of, but you'll see why I say that here in a minute. I've talked about this in previous streams. I think I was looking through the slides, I couldn't find which stream I did this in, but every object in Ruby is 40 bytes. It's a fixed, like, we've talked about how it's a fixed size, and there's really two different types of objects. We have embedded objects and extended objects. Embedded objects are objects where we're able to store the first three instance variables inside the object itself. But once we expand beyond three instance variables, we need to store them in an external buffer. So we'll say that embedded objects are able to keep their IVs stored inside the object itself, where extended ones have to store themselves on a larger buffer. So this is kind of what the object layout looks like. At the top, we have a bit field. The second field is what class it is, and then the last three fields are either the three instance variables or some information about the number of instance variables that are on each object. But the question is, like, okay, we want to introduce a shape onto this. We want all objects to have a shape. How can we store the shape on the object? Like, where can we put that? And unfortunately, we can't store it on any of these four fields, because we need to know, like, we have to have a reference to the class. We need to be able to determine the class from the instance. We could say, like, maybe let's only store two instance variables, but that would only work on embedded objects. Once we extend the object, we need to use all three of those fields. We need the number of IVs, IV list, and also the index table. So that really only leaves like the flags at the top. And what I want to do is show a layout of the object here. This is I know the slide says like 64-bit objects, but this is only a 32-bit layout. And I'm doing a 32-bit layout because Ruby has to work on 64-bit machines and 32-bit machines, which I think is fun, because I know that there are people who are deploying many fleets of older versions of Raspberry Pis to production. I'm sure all of you are running your apps on Raspberry Pis. Anyhow, we can't use these bottom three fields, and unfortunately, this flag field at the top, that's a bit field. The bottom 12 bits are being used by all objects. So these are reserved. These 12 bits are reserved. They indicate the frozen status of the object. They also indicate the generation of the object. So which, I think there's 3 generations, what generation it's in. And I don't know, various other things about objects that are common to all objects. And that leaves us with the top, what is that? The top, what's 32 minus 12? Top 20 bits. So those particular bits are used among all objects. These ones are user bits, and you can see them in the code because they're called FL user, like FL user X is the name of the macro in the C source code. And those are all available for users to use, and we decided to use the top 16 bits. So the idea is, like, we can't fit a pointer in there, but probably, like, are we going to have more than, how many shapes is a system going to have, like, realistically speaking? And what's really nice about storing it in the top 16 bits is that we can get that value back really easily by just downshifting the flags by 16 and applying a mask, and we have our shape ID for the object. So this is why we're currently limited to 16-bit shape IDs, which means that we only have about 65,000 shapes available to us total in the system. And unfortunately, that means that we have to implement something called shape GC, which it means, like, well, we're not always using a shape. So if a shape isn't used anymore, we may as well garbage collect it and then reuse that particular shape ID. And that's kind of where we are at the project, like in the project today. That's what we're working on today. We have most of the shape implementation done, and we're just trying to get GC working. So with that, I've said a lot of stuff. So I want to invite on Gemma. Okay, hold on. Let me figure out which keynote with guest. Hi, Gemma.
Hi.
How are you?
Good. Nice presentation.
Thank you. I think it's really so. So for those of us who are watching the live stream, so the way this is working is Gemma and I are on Skype, and Gemma is enjoying all of my green screen
I know, a
outfit.
green shirt.
So Gemma gets to see the full green screen setup where all of you get to enjoy a floating head.
But
So
hopefully you're seeing my body too.
yes, yes. Uh, okay, so let's talk about shapes. Gemma, tell me what problems are caused by having this 16-bit limit. Can you talk about that a little bit?
So are you asking why we need GC? Like why 16 bits isn't really enough, or what problems we're running into with the flag
What problems we're running into with the
situation?
flag situation?
Like,
Yeah.
yeah. So like Aaron was saying, or like you were saying about, I don't, should I talk to you or talk to I don't know.
I
Like you
don't
were
know.
saying with the FL user bits, there are these 20 bits, and we're not the only ones who want them. Is basically our problem, right? Like as Ruby's been in development, other parts of Ruby have taken various bits, and so right now we're running into issues where we don't there aren't actually 16 bits available at the moment for us, so we have to kind of figure out who is using which bits, and notably who's using which bits in ways that would interfere with us, and how we can kind of squash them into those remaining 4 bits.
Oh yeah, yeah. I should rewind on the slides a little bit.
Yeah.
Like right here you can see so basically like some objects are using these header bits. Like for example,
Yeah,
T
exactly.
module and T class. Those objects, classes and modules are in fact using some of these user bits. And you can see here we only have like if we're using 16 of these, we've only left 4 free for anybody else.
Yeah, and so like I think classes are using 4 and modules are using 3, but since modules are an ancestor of classes are technically like can be using all 7, which is too many for what we want to do here.
Yeah. Um So, can you tell me, like, in your opinion, what is the most challenging bit of this project so far?
For me personally, I think it's been in challenging in a fun way, but it's been learning more and more about the Ruby code base. So it's the first bigger project I've worked on within the Ruby code base, and learning more about all the different interactions and all the different kind of things that exist that I didn't even know about. Like yesterday, we were looking at refinements, which were totally new to me, even though I've programmed in Ruby for a while. Um,
I
I
don't.
don't know if folks on the stream would be familiar with it, but
I've
new to
I
me.
I've never used a refinement in
Yeah.
production. Um, yes, I'm wearing a green screen shirt. I've never used refinements in production though. Like, I've seen some code that uses them, and the code was basically like amazing hacks, which I
Oh, nice.
we should talk about it on the stream at some point. Amazing hacks with refinements, but yeah,
Like monkey patching hacks, or
yes.
what
Well, it
was?
was
Yeah.
the one that I'm thinking of is one that John Hawthorne did. I can't remember the details of it completely, but it was basically like um, we want to insert symbols into a hash table of strings, but we don't want to like do method lookups or something like that. I can't remember the optimization he did, but it's really amazing, and I should put it on the stream at some point. Um, I wanted to say the thing that's been most challenging to me so far is dealing with GC stuff.
GC has definitely. I always try not to like bias myself by the problem we're currently working on, but I feel like solving GC
So
has been
so
tricky.
So for folks watching the stream, basically, since we want to GC these shapes, it means that we have to have essentially weak references to the shape. So we'll create a shape for a particular object, and remember when we look up the object or when we look up the shape, we need to make sure that that lookup is very fast. So the way that we do it is we store an ID for the shape, and then we have an array that we store all the shapes in, and the ID of the shape is actually the index into that array. So we basically say like, oh, if we're looking up shape 4, like if shape 4 is stored on an object, then we look up the shape object by saying like index into the array at the fourth index. And that array has to be a weak reference array, and that's just caused like
So many issues.
yes, many issues for us. Okay,
Yeah.
so what is the most fun thing about the project?
I think it's been really fun for me to learn from you. I know it sounds like a funny answer, but no, it's true. I think learning is one of my favorite things, and I think it's been learning, like introducing a new feature or a new way that Ivy caching will work into Ruby. But it's really, it's just been fun to learn my way around this code base a bit more. What's been fun for you?
What has been fun for me? Well, I like this project. I think this project is very interesting because I think that we can get well, one thing I didn't mention in the slides is like we're able to get we may be able to get good speed improvements on the existing implementation, but what's really cool is we'll be able to use these shape IDs inside of the JIT as well, so we can use that for making the JIT even faster, which I think is very exciting. So I also like this. I also like this project because like so working on a JIT is basically like making machine code at runtime. Like you're putting together machine code at runtime, and that makes my brain like hurt. So working on a project where we're just doing like compiling stuff and trying to figure it out, like that's what I enjoy. And to be honest, I actually enjoy the GC, like debugging the GC stuff. Yeah, it's extremely challenging, but it's like it's this weird like puzzle you have to solve, which I think is fun.
We've gotten some of the like deepest bugs I've seen in a long time where it's like, oh, like each day we'll learn like one more thing or one or two more things about it, and it's like some good bugs in there.
Working on the refinements thing yesterday was very interesting because I liked looking at the different flags that modules were using and trying to figure out like, okay, are these actually like how are these used in particular? Like how is this how are refinements actually implemented, which is a fun thing to look through. All right. Let's move on today. So what are we working on today? Gemma. Oh, should I introduce it?
Uh, yeah, if you want to go
sure,
ahead. Yeah.
Sure. So today we're going to take a look at like there's a couple things I want to look at. First off, I want to show off like I would like to take a look at shapes themselves. So one of the things that we did to make working on this project a little bit easier is that we made a Ruby interface to shapes. So we're able to say like, hey, tell me what the shape is for a particular object. The other thing we can do is that entire transition tree that I described in the slides, we're able to dump the entire transition tree. So I'd kind of like to show that off in the code. Like maybe we'll look at that.
Yeah, show off like how we've exposed that, and
yes,
that'll be a good visual on shapes. Yeah.
And then the other thing I'd like to work on too is as we're debugging these shapes, we don't have any support in LLDB for inspecting the shapes themselves. So what I'd like to do is like poke at the LLDB scripts and see if we can get LLDB to expose a shape. So basically we'll say like, hey, print the shape out, and then it'll show, I don't know, more info about it. How does that sound?
Yeah, no, great.
All right. Yeah. Then let's code. I'm going to switch over to the desktop and get Keynote out of the way. All right. And I need to put you here. That's wrong. Desktop with guest. There we go. There we go. My floating head over a terminal.
Okay, so everyone can see the terminal now?
Yes. The thing I'm really excited about, like, I'm going to wear this green screen shirt all day. So the rest of the meetings that I have today are going to be
Green screen.
very enjoyable.
Have you worn it outside ever? I feel like that would also
No.
be quite funny. Wear it to the coffee shop.
I need to get some. I need to get some like ping pong balls and stick them to my face and go to the coffee shop.
That'd be good.
All right.
Cool. Should we just write a little? Maybe start with like writing a couple of classes similar to what you had in your slides that'll demonstrate.
Yeah. Let's look at some. So let's do some, green mustache. Yes. Let's do that. And by the way, if anybody watching the stream, if you have questions, just put them in the chat and we'll answer.
Actually. So if we did like super whatever, something like this maybe, and let's get one more that also, so we get 2 edges out of A.
Yeah, that sounds good.
So something like this, and so the thinking is like if we called A.new, we'd get a shape on A, B.new, we'd transition, like Aaron was saying earlier, we'd get this A equals 1, so we'd get the A shape, and then we'd transition to a new shape.
Mm-hmm.
And same with like C.new. And we exposed that through a method that I think we called debug shape.
I forgot.
We'll see. I think it was this. Yeah, so let's see what we get.
Oh,
okay.
Cool. Nice.
Cool. So we got our 3 shape objects, which we just printed the objects themselves, so you can't see much. But if we could print the ID on them, and then maybe if we print like the edges on A after it has a few. I don't know what's helpful. So
yeah, that's awesome. Yep.
So something like this maybe. So if we let's print the ID on all of these actually. So we're making a new A, a new B, a new C, and like we saw here, C and B both define that A instance variable first.
Mm-hmm.
So then if we run this, we see like our 3 shape IDs. It starts at 11, which might be confusing, except for that like Ruby's just creating a few objects as this program is starting. So those are getting our earlier shapes, shape IDs, like it's 0 indexed. And then the edges, we can see we get like, so the shape that has just the instance variable A has 2 edges going out of it. One with the instance variable C to this new like C shape, and one with the instance variable B to this new B shape.
Can I see the code again?
Yeah.
Okay, so the instance. I see. Okay, so we have A, and A has a shape, and the possible outgoing edges for A are B and C. Because we instantiated B, so we created a new instance of B and a new instance of C, and those 2 populated outgoing edges for A.
Yeah.
That's awesome. Yeah. Okay.
Yeah.
Okay.
Is there other stuff you want to look at here?
Let's do a freeze one. Let's freeze one.
Oh, nice. Okay. See that new dot. Oh, yeah. Let's do this actually. So if we just do C.new and we get the ID and then C.new.freeze, we'll see here, let's get rid of this so it's clear. So we have like a shape with just C.new and a shape C.new.freeze. And we can see they're like 2 different shapes, the frozen C. And we can, I don't know what, so you can make as many of these frozen Cs as you like, and they'll all have the same shape ID, which is that easy comparison you were pointing to earlier of like just having to compare the shapes and not having to look at the frozen attribute.
Let's do an instance variable set on one. Let's see that too.
What is it? Set instance variable? I
think. I can't remember. No. It's instance variable set. It's instance variable set. Sure.
Oh. Ignoring
Whoops.
that. Oh, this is okay. Okay.
Oh, what is
So
this?
Aaron and I think this is maybe some of the GC stuff.
Should we do?
So,
Okay, should we do LLDB stuff or should we debug this?
whatever you would prefer.
Let's debug
We
this.
haven't touched frozen stuff in a while. Yeah.
Yeah,
Okay.
let's
Cool.
debug this. Like, what is
We
the deal
haven't
here?
touched frozen stuff in a while, so
What does instance variable set return? I don't know. What does instance
wait,
variable set return?
Oh, it's not. Oh, that's
Oh!
just not a shape. That's fine. Yeah. You're right. Good call.
Good call. Thank you. Yes.
Did someone say that on the
Yes,
stream?
on chat. Yes. Thank you, Mia.
Thank you. This is great. This is the pressure of live coding.
Yep.
Cool.
Okay. Now
Thank
we
you,
see it.
Mia.
I mean, let's at least fix that. Let's fix that boog.
Fix
Debug
fix
shape.
that.
Yeah, it's clearly a bug in debug shape. Let's fix it. Instance variable set. What is instance variable set return? We got to check that. Just print it out in the script and let's see what's up. It's probably returning the 2, I would guess.
Yeah, I would guess too.
Ooh.
2.
Yeah. Okay, so when we do in debug shape, we need to check the type.
Yeah. I don't know. I think we define it in gc.c.
vm.c.
Debug share.
C.
It was in vm.c?
Yeah. I saw it.
No. I think that might be commented out. I think. Oh, no, you're right. Okay. RBObj, debug shape. Cool. Yeah, so here.
Yeah.
Yes. Yeah. So,
and we don't,
like 2. Yeah.
Do we have shapes set on numbers?
No. I think that's probably where we're crashing, but we can actually, why don't we look at the backtrace and we'll see exactly where this is.
Yep. In get shape ID.
Yeah.
Yeah, we can't do that.
I feel like we don't also yeah. So we can kind of raise on within get shape, or we can raise right here on RBObj debug shape.
Mia's asking, so everything is an object, but not every object has a shape. No, I think the correct answer is that every object should have a shape. I don't think we should raise. I think we should have a shape here. The thing is, I think, can you check, what is this? I think we need to fix get shape ID. So we need to check if it's a special object.
Yeah. So here.
Yeah. If before the switch statement, we need to check like if.
What's it?
I don't remember.
So that didn't it say it here though?
Yeah, it did.
Which frame? 6 maybe. RB special const p.
Yeah, that's what we want. Perfect. I think so. Special RB special const p returns. So special constants are all the ones that are like immediate. So Q nil, Q true, Q false.
Rules.
Yeah.
Are
they? Can you pull up IRB? Is nil frozen? I want to say no.
Yeah.
Nice.
So nil is wait, it's true frozen?
Yes.
Oh,
good.
Interesting.
I like this. How about false? Yeah, his numbers are definitely frozen.
Nice. So these you didn't. I guess you didn't mention the root shape on the slides. Explicit by that name.
Yeah, I mentioned the root shape, but I didn't talk about the frozen, like the frozen shape. So
Yeah.
one
Okay.
like one optimization that we've implemented is when Ruby boots, like tons of objects are frozen. Like
Mhm.
if you put at the top of your script like um frozen string literals, like all of those strings are frozen, and if we were to do that, like in order to implement that, we'd have to be like, okay, we'll create a new string, then we got to do this transition, and we don't want to implement that transition for every frozen string literal because that'll slow everything down. So what we
Yeah.
did is we pre-allocated a frozen, like a frozen shape. So if something comes to life and then is immediately frozen, then you just get this special frozen shape.
Yeah.
And
And we called it frozen root, so it's pretty explicitly named, I think, in that it's just literally the root shape
yep.
frozen. Yeah.
So I think that's in these cases, this is what we should do. So for special consts, we should just return the frozen root.
Return get frozen root shape.
Yep.
But we want the shape ID.
Mia says frozen shapes should be called icicles because it's root shaped.
I love that. If they'll take it, we'll
Yes.
definitely go for that. Cool. So something like that.
Yeah.
And then we can rerun.
Uh-oh.
Previous implicit description.
Oh, do we need to move the function up? Is it
Wait,
too
what
low?
is get? Get frozen root shape returns a shape. Oh, no. Is it too low?
Is it not in the header? Previous declaration. So it's
Get for oh yeah, it might not be where it needs to be. We have get root shape.
okay.
So yeah. Frozen root shape.
The thing I like about this green screen shirt is that you can really see like the contours of my body. You can tell I've been working out.
I love the image of people at the gym in green screen outfits. Dude, I would get so hot in that, like in a turtleneck.
It is. Let me tell you, it is. I'm suffering for my viewers right now. It's quite warm in here. The shape of Aaron. Yes, this is my object shape.
Okay, so this is just recompiling.
Go, go, go. Beauty is pain, yes.
These comments are funny.
Yes, this is why I enjoy live streaming the comments.
Yeah. Definitely not a frozen shape over there if you're getting hot.
No, no.
All right, yeah.
Nice,
okay, great.
nice.
No more crash.
Yeah, I like that.
Yeah, that was good. That was great. Should we look at adding that LDB helper?
Yeah, let's do that. One sec though. Let's look at like I want to show off. Let's just do like a get shape ID or get shape with an immediate, like do it on true.
Yeah.
And we need to add a test for this.
Oh, we definitely need to add a test for this. Ruby VM.debug shape on true.
Yeah. So that should just be the frozen one. Nice.
Yeah,
nice.
and I think it's like ID 1. I think. Yeah.
Yep.
Nice.
Cool. Okay. Let's add a test and then dive into LLDB.
Where did we put the shape? Remember where this is gonna be too much. Do you remember where the shape tests are? Yeah.
No.
Okay.
Just grepping.
Yeah, I'm
Test.
frozen because I did. Yeah, okay. Grab shape test. No.
Test Ruby test shapes.
Yeah.
Nice.
Cool.
Oh, we still have the shape ID method on object space. We should maybe remove that.
Yeah. That's a good call because now we expose it through Ruby VN.
Yeah, because we can get if you can get the shape, then you can just get like we can get the ID off the object.
What do we want to assert? What do we want to assert here? Like,
just,
yeah,
just
go ahead.
that we can get the shape. I don't think we want to assert the ID because maybe the ID will change.
Yeah.
Just be like, just do assert.
Yeah, go ahead.
Just do assert.
Object space.
Yeah. Is that gonna work? How is shape ID implement? I don't know how this is implemented.
Yeah, we want Ruby VM debug shape.
Yeah.
Yeah, we haven't been through this. Yeah, code in a minute. Okay, what was it called? Ruby test shapes. Test shapes.
Nice. Nice. I got new switches for my keyboard, but I haven't been typing. They're quite loud.
Different sound? They feel the
Yes.
same volume. Sound the same volume to me. Nice.
All right, we passed that. All right, let's add let's update the LLDB scripts to deal with Jack is asking what switches they are. I forgot. They're Kayla. I'm not sure how to pronounce the company's name. They're Kayla White something or other. White Owl, I think. Owl's in the name. V2. I got them because they have a click bar and palm plastic. I'm sorry, I'm nerding out about keyboards.
You're fine. I know nothing about keyboards.
I know too much. Okay. So we want to add support to the LLDB scripts. Let's do.
Yeah.
What is
yeah.
What is the easiest way to do that?
What if we? To like actually do it or to get into the LLDB script?
I want to get into the LLDB script. So
why
we need to like.
Why don't we break on? Or yeah, go ahead.
You go.
What if we just put like a print on a certain shape ID or something, and we can just break there, and then we'll get the object on like get next shape or something. Does that make sense?
Yeah, that makes sense. Yeah, let's do that. That seems fine.
What were you thinking?
Basically something similar. I was gonna say we could like call debug shape and then break in there, but that's fine. Doesn't matter.
So this is I guess the code that's like getting the next shape for a given shape.
Oh yeah, why don't we walk through this so folks know what's going on in here?
Oh yeah, cool. There are definitely some debugging prints in here at the moment, but we can just communally ignore them. I don't know how else to say that. This is not pretty. Seeing how the sausage is made.
Yep.
All right, get next shape internal. So the caller, it's a static method. For those who are unfamiliar with C, it means like we're calling it from within this file. So we can see the callers here are get next shape, and I think this is like get next frozen shape or something.
Yeah, this is the special
transition shape frozen.
Yeah.
And so the one we're kind of focused on is get next shape, which is going to pass in as its third argument. So the shape that it already has the ID, which is like the instance variable that we want the next shape for. So it's if you're calling instance variable set with a new instance variable or something like that, or just setting an instance variable, the ID is going to be that instance variable, and then the transition type, which is like an IVAR transition in this case. That makes
Jack says when I do debug prints, they're usually boop or morp, so yours are very nice.
Thanks, Jack. I'm like very grateful. These are the pretty ones. What was the funny one I had the other day? And you were like, "What does this even mean?"
I don't Mia, we're using Teammate. We're sharing with Teammate. So this function is given the current shape, I want to go to the next shape for this particular instance variable. So the ID is our edge in that tree that we saw.
Yeah. So the first thing we do is we look up and we say, "Hey, if this shape already has the ID." Like, yeah, this comment is actually good. We can all read this comment. If the shape already contains the IVAR that is being set, we'll return the shape. So if the shape like already has the ID, we don't have to do anything else. Great, just give it back.
So that would be the case where you'd say like, I'm going to set IVAR A, then I set IVAR B, and then I'm going to set IVAR A again. We don't want to have another edge from B to A because we already had an A. So this hash table essentially prevents us from having cycles or repeating.
Exactly. Yeah, and it obviously makes things like cleaner and faster too. This is so if the shape doesn't already have any edges going out, like if this is its first new IVAR, let's just make that ID table. And then this is kind of where something important happens here, which is if we already have that transition. So if, say, we're at like we have, I can open this. Say we're like here, right? So we already have our A. Say we do b.new and then b.new again. So we've already made this transition from just having the instance variable A on a shape to a new shape with the instance variable B. We make that here. And then the second time we make it is where we just were. If it already has the ID, like great, then we don't need to do anything. We'll get to that case. If it doesn't already have the ID, I don't. Do you want to get into this garbage object stuff?
No.
We can talk about it. It's okay. We're gonna ignore it. That's big hand wave at the end of this if. But yeah, I feel like that's more than the time we have left. Okay, so if we haven't already made a transition, this is like similar ignore GC stuff. We're gonna get a next shape ID. So this is where you can think of if we're like GCing shapes. We haven't implemented this part yet, but if we're GCing shapes, we're gonna have shape IDs we can reuse. So we need this like give us our next valid shape ID function. This part is interesting too. So if we're at this, we have, like we said, 65,000 shapes, and so roughly 65,000 shape IDs we can use. And so at some point, even with GC, it's feasible we could run out of shapes. And so we're saying if the next shape ID it's giving us is the max shape ID, which is telling us like we've used all of our shapes already, we have this no cache shape. And the point of the no cache shape is just saying like, look, I'm not going to tell you anything about your IVARs. This is like the catch-all out of shapes.
This is like everything works. You just don't get to cache. Sorry, you don't get to cache anything.
Yeah, sorry, you are very slow and also have a lot of shapes. But this is go ahead.
We should mention. So we've run this against like I don't know about you in the audience, but think about now that you understand that all these shapes form a tree, like how many shapes might you imagine are in an application? Like how many shapes do you think are in an application? And Gemma and I have been talking about this a lot, and we can't, it's not intuitive. We can't figure out like what the number would be. So for example, we ran this against this fork with all the benchmarks on, what was it?
On Shopify's
I was
Shopify's monolith were you talking about, or you were talking about well, we ran it on Rails
discourse.
bench. Oh, Discourse too. Yeah, yeah, yeah.
Yeah, we
We've
ran it
run it
on
on Discourse.
Discourse gave us about, what was it? It was like 4,000, right?
Yeah, 4,000. Yeah.
Yeah, there were only
Yeah, yeah, yeah.
4,000 shapes in Discourse. We ran it against our CI, and in the CI process, at the end of the CI process, we had to print out like how many shapes were there before you exit. How many did we see there?
The most we saw was 40,000, which is like there's still a little breathing room before 65,000, but it was close enough for us that we were like, this is worth doing GC and figuring out how to not get much higher than 40,000.
Yeah, so Ryan says, "Wait, that's it." Yes, we were surprised. We were surprised too
Yeah,
because like sixty-five
yeah,
thousand seems like not a lot.
yeah. It was also one of those things for us, at least we talked about this a lot, where it was like a big number that it was hard to conceptualize. Like, what does 40,000 shapes really mean?
Matthew is asking, at shape GC time, could you kick rarely shaped objects into no cache to free up their slot? Rarely shaped objects.
Oh, so Matthew, are you saying like if there's only one object with the shape, say? Or if
Oh,
it's like a kind of leaf shape that's like down a long path that doesn't get used a lot?
that's interesting. So if you had like a
Yeah.
singleton, like on app boot, for example, you have a singleton and then no other code path goes down there. Yeah, that seems interesting.
That is interesting. Yeah, and we definitely have like debugging tracking around how many that we can do around how many objects is shape. I don't know. The shape bits are pretty squeezed as is, so we would have to figure out how to get that count in
Yeah,
to a shape in a feasible way. But it could
yeah,
be really interesting.
yeah. We'd have to do the bookkeeping. That's a really interesting idea. I like that.
Yeah.
We should investigate, but we need to get before we investigate that. We need to get this to stop crashing.
That is our immediate to do.
Yes.
Um, okay, so we're now in this case where we're like at a shape ID that we want. That's good. That's not the max shape ID. We don't have an edge out to it. So we need to actually make a new shape here. This is an assertion for debugging. We're going to allocate our new shape. And this line is important. So this is saying we're going to copy each shape tracks which which instance variables it already has. So if we're making a new shape from an existing shape, we want all those IVs to copy over, right? Because we'll necessarily have those, and then one, which we'll get to in a second. This is going to insert our new shape into the previous shape's edges, so that next time we do a lookup like this, it'll be true, right? We won't have to create a new shape. Do you want to get into right barrier stuff? I don't.
Nope.
Hand wave. Okay, that's a hand wave. We're gonna set shape by ID is gonna say, hey, we have this new shape. Let's put it in our shape list, which is on
The
the
big
VM,
array.
so that
Yeah.
the big array of all our shapes. Yeah, yeah.
So like we were saying, there's
Um,
two main data structures really. There's the tree of shapes, and then we have an array. So the tree is so that we know how to get like how we made those transitions, and the array is so that we can do a fast lookup of the shape given a particular object.
yeah. And then, so this is saying, like Aaron was saying, we can pass properties like we just looked at and debugged a little the frozen property. So that we pass as our transition type into this method. So if it's an instance variable, we want to insert it into the IV table, which is this thing that we copied that'll have all the IVs up until that point. Now we want to put our new ID into that IV table. And if not, we're going to freeze the shape. That means it's a frozen transition. Just set res to our new shape. And then ignore debugging. And then we can... I'm so grateful these are just like sane print lines too. There's nothing wrong with that. Res is a garbage object. Great. Could have gotten very embarrassing very fast. And then return, yeah, our new shape. Are there? I can't read the comments, but Aaron, do you see any questions
No,
there? Any? Okay.
no questions. However, we we are totally out of time. I have a
Nope.
meeting.
That went so quick.
It did. So we're not I'm sorry, we're not gonna do the LLDV script today. I
Yeah.
apologize. All right, I'm gonna switch us back to the keynote. Thank you, Gemma, you're still on. Thank you so much for being on today. I really appreciate it. Also thank all of you for coming and saying hi to me, and happy Friday, everybody. I have to go to a meeting now. Thank you. All right,
Thanks, everyone.
bye.
Bye.